So what I'm going to talk about is actually a bit more a generic view rather than the concrete examples that Pat just showed. And this summarizes numerical simulation work we have been doing over the last 15 or so years. So this will focus on the geologic and physical controls on supercritical or superhot systems. And it will give a bit of background how they are linked to conventional high enthalpy geothermal systems, at least how we think they are connected. And among the insights from numerical simulations, I will talk about the important role of how the brittle ductile transition in the broadest sense controls where they are and how hot they get. And then also about the links between conventional and superhot resources. Now, quite a bit of this work will come from Sam Scott's PhD thesis he did back then with me, and he will be talking later on something else he has been done in the meantime. And what I'm giving here is sort of a very basic introduction to that. Quite a few people in the audience may have seen that before, but experiences like 2/3 at least haven't seen that or don't remember it. So I will try to give a base here of what we're talking about. This will then be followed by the talks of Alina and Benoit, who will show the more recent stuff we have been doing on exploiting this. And so, yeah, since Kenny gave the IPGT intro, I will also like to say a lot of this work was under the umbrella of IPGT, so that helped a lot making the connections to Iceland and New Zealand and so on. Okay, let's start with some very basic thing. We're talking about supercritical, and then we hear about superheated and superhot. And there's always a confusion what is meant. And this is actually intrinsic to the problem. You can't do anything about it. So this is a phase diagram of water in temperature on the horizontal axis, pressure on the vertical axis coordinates. And I guess most of the people in the audience know that there is a boiling curve that ends or terminates in the critical point at around 374 degrees C. Now, when you're at temperatures below the coordinates here or pressures below, then it's easy to distinguish liquids here and vapor or steam here because they're separated by the phase boundary here. But as soon as you go to anywhere outside this, you can actually transition from vapor or steam here, make a circle around here, and you will not encounter any phase boundary and go to a liquid phase. And these different lines here with numbers that are isocores, so lines of constant density in kilograms per cubic meter. So this here at room conditions, it's about a ton per cubic meter, and then here in the vapor region, maybe 50 grams, and the critical density of water is 322. So you can transition across here without hitting a phase boundary. And so by definition, there is no phase boundaries for anything like a supercritical phase or so. It's simply not a defined thing. So there is no rigorous definition possible because you have transitions here that are just gradual. And whatever you call supercritical will be by convention. So some people say supercritical is everything at a temperature higher than 374. Others say it's just the upper right quadrangle here, and yet others come with pretty exotic things that anything that has a pressure higher than critical and temperature, or temperature higher than critical, so everything here would be supercritical. Again, it's only by convention. And the same problem would be for superheated. You would call a steam superheated if it is to the right of the boiling curve. But then let's look at the 100 kilograms per cubic meter isocore here. If you followed that, you would end up somewhere at pressures higher than critical, but the properties of that fluid wouldn't have changed a lot. So there is no particular reason why this should be called superheated down here and then supercritical up here. So again, keep in mind, there is no unique definition that has a rigorous physical base. So then people introduce superhot as the most generic. I think this is fine. And you can, again, introduce different versions of that. So superhot version 1 would be temperature higher than 374. Or in a different phase diagram, now pressure going to, on the vertical axis, increasing to the downwards. specific enthalpy on the horizontal axis. This would be the liquid plus vapor two-phase region, which would be the boiling curve in these coordinates. Here's the critical point. And everything to the right of that at very high enthalpies could be called superhot. So if you move upward here, if you depressurize, you wouldn't touch the liquid plus vapor dome. You wouldn't condense liquid out of a dry steam. So these are nice, but they are not identical. If you project the yellow one here onto the other one, you see it's this yellow thing which doesn't agree with the orange one. So again, we are facing the problem, they are not identical. So pragmatic, I advocate a pragmatic use to use supercritical or superhot synonymously to any temperature higher than critical temperature of water, so higher than 374. Pressure is typical for geothermal reservoirs. And then if you like to put additional constraints on enthalpy, permeability, and communicate your definition of that, so then we know what we are talking about. So having said that, some problems. Moving the slides here. Okay, so high enthalpy geothermal systems. This is Krapla in Iceland. You see the steam coming out of the power plant there. And what is beneath, somewhere there's magma. So this is a very, very schematic conceptual model of that, generic one. There's a magma body at depth. And this heats groundwater that is in the upper crust. It gets less dense, and so convection is induced. Normally, in these systems, the water gets so hot that on its way up, it will somewhere hit the boiling curve and will start boiling. Now, the water that's circulating, I said, it's typically meteoric water, so rainwater, river water or so that trickled into the crust. And the production temperatures are typically somewhere between 250 and 300 degrees C, producing mostly from the upper 2 kilometers. Now, if you drill into that, it looks roughly like this. Again, idealized case. So on the horizontal axis is temperature, vertical axis depth, and you would follow this red curve here, which is known as the boiling point with depth curve, reflecting that the boiling pressure or boiling temperature of water is a function of pressure and vice versa. As pressure increases downward, so will the boiling temperature, and it follows this curve. Some systems boil to great depth, like 2 kilometers. Others boil only in the upper few hundred meters and then have a nearly isothermal upflow below. And we will see in a few slides down the road what is the reason for that. So it's mostly a question of how high the enthalpy content of these fluids is. If the enthalpy, the natural enthalpy content of the system in the undisturbed state is higher than 1600 kilojoules per kilogram or so, you would be boiling to great depth. If it is lower, just over 1100 kilojoules per kilogram or so, you would be boiling only in the upper part. Let's have a look what that means here. Here's the enthalpy. This is the boiling curve, and this is exactly what I said. If you have 1.1 here, you hit it here, and that's between 200 and 300 degrees C. And then you boil at a pressure from 400 bars or so, from 40 bars or so, or less. So that means only in the upper few hundred meters. If you have a higher enthalpy, you hit it at higher pressures further down, so it would be boiling to greater depth. So the conventional resources that are produced at 250 to 300 degrees on this diagram are somewhere here. But then the magmatic heat source that drives the whole thing has a temperature of, say, 800 to 1200 degrees C. So there's quite a discrepancy in there, and the smart Icelanders 20 plus years back thought, well, there must be something hotter in between. I mean, let's go back. When you look at this boiling curve with depth, you see you don't gain a lot of temperature when you drill deeper. And that's probably the reason why people didn't drill deeper. But if you think this is like 800 to 1200 degrees C, there should be something interesting. And so IDTP's goal was to reach something initially at least 500 degrees C and 300 bars, somewhere here on the diagram. And you see if you depressurize it, you will never touch upon production of the liquid vapor field. So you would, in the ideal case, even get dry steam at super high enthalpies directly out of the well. So then this is the view we had, a magmatic heat source, circulating water. In convention, if you want to study this with numerical simulation, you need to be able to include all this here. The conventional reservoir engineering modeling is something like this. You exclude this part, you manipulate the boundary conditions until you match what you observe during production. That's super useful for conventional reservoir engineering and operation scenarios. But if you want to understand super hot resources that may be here above the magma chamber, this is definitely not the way to go for. So this conventional approach is not sufficient for that. And so for meaningful simulations, we need to add about supercritical resource, we need to add functionality. And so this was pioneered by Dan Heiber and Steve Ingebrigtsen from the USGS 25 years back. And they actually were able to include a hot body mimicking magma in their models. The heat transfer mechanisms are conduction and convection. The full water properties up to magmatic conditions were in the model. That's crucial to include boiling, supercritical behavior, strongly temperature-dependent, pressure-dependent fluid properties, and so on. And if you have two-phase boiling flow up here, it's different from the normal oil to oil-water two-phase because there are some thermodynamic relations linking steam and liquid. So that has to be included as well. And the key thing, really the key thing, and Pat mentioned Bob Fournier's work, is to realize that down in your heat source here, you have no permeability because it's very hot, partially molten maybe even, so you have no permeability there. It's ductile, so due to the load that is on there, any permeability, any pores, any fractures will close. And so in this part where it's where it is really hot, you have conductive heat transfer. And outside, where it is permeable, you will have convective heat transfer dominating the thing. So what Dan and Steve back then implemented is a temperature-dependent permeability model to include this. So on the horizontal axis here, temperature, vertical axis log permeability, and they considered quartz-rich rocks under normal crustal strain rates, which then would have more or less constant permeability up to about 360 to 400 degrees C, and then you would see a very rapid decay of permeability or decrease down to basically impermeable at 500 degrees C. Now, these temperatures are a function of rock type, of strain rates, tectonic regime, and so on and so on. But this was the initial study that worked with these particular setups. And this was pretty important to do this. And another one, you have to have the model big enough that the boundary conditions of your simulation would naturally evolve, that you don't have boundary effects. And so when you include all this, then the system scale permeability is the main variable that is you can study in your science here. So this is from Sam's PhD thesis back then, and so he did it with a bit more advanced technology 20 years after Heiber Ingebrigtsen, using our own code here. And you see here is an elliptic magma chamber intruded into some rock with some properties. And then we looked at what is happening to the system. And so now we have some hot intrusion here, intruded into something that was relatively cold. And now the hydrothermal or geothermal system has to evolve. So it first goes through an incipient stage. So the groundwater is being heated near the intrusion and starts to rise. But on the way up, it has to heat the rock. So this rise is retarded. The isotherms need quite a while to move up. That can take a few hundred, few thousand years, depending on permeability. And then it transitions into a main stage where the system is fully evolved, the plume has reached the surface, you have boiling, and so on and so on. In this particular setup, this was after 3,000 years. And now, unless you recharge the magma body with new magma, it will cool. You have cold water coming down here, and it will mine heat from this body, feeding this hydrothermal system. And at some stage, this heat source is exhausted. So what happens now, you're in the veining stage, there is no magma body there that is molten or so. And actually, the rock on top has been heated by the previous stages, and now you start cooling from below. So instead of having the boiling curve down here increasing in temperature with depth, you now have this inverse shape in the deeper parts, while the upper part can still be boiling. Okay, so this upper part can be boiling, and it is indistinguishable from the part, from the stage where you still have the magma body. So if you have a hot system in the upper 2 or 1 kilometer, it doesn't tell you whether you have a supercritical resource down here or whether it has already gone 1,000 or 2,000 years back. Now, one thing to keep, what is poorly understood at present is the role of fractures and faults. We haven't it included in these types of models yet. It's a work that will come soon. And also the style of the magmatic intrusions, whether you have dikes coming in all the time or whether you have flat sills here or end on end. All this has not been studied systematically yet. But one thing to keep in mind when you see the numbers here, so magma-driven systems are highly transient on geologic time scales. It's nothing that's sustainable for 1 million years. It's just a few thousand, maybe a few tens of thousands of years that you're facing here. So then another finding, if you do these simulations, again, we have the pressure enthalpy diagram, then you see the permeability, the bulk permeability of your system here determines what the temperature is that you get. So if you have a pretty impermeable setting like 0.1 millidarcy, what you see, the different lines here are the thermal structures along the vertical profile here above the heat source as a function of time. And what you see here is the evolution from early to late, and you see basically a conductive profile. So heat transfer by convection doesn't play a role at these permeabilities. It's basically conduction only. If you increase permeability by just 2 orders of magnitude, so for groundwater people, this range is essentially nothing. In geothermal, it's all the difference. So 10 millidarcy. In the hottest stage, you see boiling in the upper 500 meters and isothermal upflow below, so they don't get hotter than 240 to 50 degrees. And in the diagram, this is something like more or less straight upward flow here. And in between the two, 1 millidarcy, you get the hottest systems. They are boiling down to 2 kilometers. And what is the reason behind that? Well, it's this competition between conduction in the heat source and convection in the permeable rock surrounding it. So conduction is pretty limited in its efficiency, but if you have high permeability, you're cycling a lot of water past a limited heat source, so it doesn't get that hot. If you cycle somewhat less water, it can pick up a lot of heat here, and on the way up, it's still fast enough not to lose it. That's this case. And if you have very little permeability, flow is very low. So water will just get heated according to the conductive thermal structure here and passively rise and lose its heat again according to the conductive profile. That's what you see here. So that's one of the key features to keep in mind for these systems. The thermal structure basically indicates what's the overall permeability of the system. If you have 10 to the minus 13, you have no high enthalpy resource because then you get only 120 degrees or something like that. So you need anything in this range to make it work. So bulk permeability of about 1 millidarcy makes the hottest reservoirs. Now the link to the supercritical resource, again from Sam's work. And he investigated here where permeability starts to decrease. 360 for quartz-rich rocks, 450 maybe for intermediate rocks, 550 for basaltic rock. And it's immediately clear if the permeability decreases only at 550, then waters can access hot rock below this temperature. So the likelihood of getting a reasonable supercritical resource is much better for settings like that, where you have, for example, basaltic rock or you're in an actively extending regime. On the vertical axis is 1 millidarcy, 10 millidarcy permeability. And so the reasoning is the higher the brittle ductile transition is, the more likely it is that you get one of these orangey supercritical resources, and the lower the permeability overall is, the bigger they get. But then the flow rates are lower. But anyhow, the key thing is it seems as if they are an integral part of these systems sitting near to the magma body. Now, so one of the things here is, again, permeability affects the size of and the flow rates in the superhot resource. And that, of course, needs to be understood if you want to explore for them. Because if you have a tiny thing like this, it's much more difficult to hit with a well than if you had a bigger one like this. But the bigger one has lower flow rates, very similar. All right, I rushed quickly through IDDP1, was drilled by IDDP 13 years back. And they got these super hot stuff coming out, 450 degrees C, 140 bar at the wellhead. And for Icelandic geothermal systems, it would give a very high electric power output of 35 megawatts, so very interesting. Then with Sam's model, just made super simple assumptions: a magmatic intrusion at 2 kilometers, basaltic host rock permeable to a higher than 500 degrees C, and otherwise let the model evolve. These are the results. Again, pressure here, enthalpy here, and for a 2 kilometer intrusion, 2 kilometer deep intrusion, which was what was drilled there, you get this type of thermal structure just above the magma to the surface. And IDDP1 conditions sit right on this model thing. So we thought that given this, we are probably catching most of the geology and the physics of the process with a simple model that we have. So now the question is what to do with this, because you see, you have a shallow magma, you would inject water into it, you would cool it probably. And you would drag in, so if you inject here cold water, you may actually depress the superhot isotherms pretty rapidly. Is that a good idea? We don't know. Direct production might have the same effect by dragging in water, cooler water from the side, bringing it down. So we now need to model how to utilize it. How would we disturb the system if we put a well in that? And Alina will give you some very first results on that in the next presentation. Now, then another question was, back then, before IDDP2 was drilled, there was a IDDP workshop at Reykjanes, and back then this was the sketch. So the reservoir in Reykjanes follows the boiling curve with depth, and then has these near iso-enthalpic upflow for the natural state around 1300 kilojoules per kilogram or so. And then there was speculated that below is this 3000 kilojoules per kilogram system below. And back then there was a paradigm that flow in these systems is more or less isenthalpic. But how can you then get a 3 megawatts or 3000 kilowatts per kilojoule per kilogram system below a 1.31? Is there some tighter formation in between or not? Or is there something else going on? And then Sam actually, in our model, introduced a virtual tracer to the simulations. So every packet of water that was cycling past the intrusion here got 100% supercritical tracer, virtual tracer, if it was under supercritical conditions here. And then he followed how this thing would disperse into the overlying conventional system. And you see actually orange is the 100% tracer, and it gets diluted, and it means nothing else. This is by no means isenthalpic upflow. You just mix in colder water from the side, and by this dilute the temperature, so to say. You can turn this around. I'm also more in the mineral side of things of hydrothermal systems. And there you have this thing that is called vectors to ore. So in terms of supercritical resources, the thermal structure in this sense would be a vector towards the supercritical resource. So this could, following this, and there can be pretty complex patterns. I can't go into the details of that, but it has exploration implications, and this should be considered if one is trying to drill into one. So The key message here is superhot resources are hydraulically connected to the overlying conventional reservoirs if the heat source is not yet exhausted, because then you can have the superhot resource. So to wrap up, so I think with these rather simplistic simulations, we have unraveled the modus operandi of high enthalpy geothermals, and it needs an adequate, even if it is just generic representation of geology, physics, and materials properties. That's really crucial. And superhot resources appear to be an integral part of such systems, and their occurrence is mainly controlled by the rock properties and the time within this highly transient evolution of the system. So how to utilize and operate a resource is still a matter of research. We have now some advanced well models that will be shown in the next two presentations by Alina and Benoit. These well models are for different purposes, so they will target different things. And these will be applied in the preparation of IDDP3, because there have been some nice well tests at a test site with IDDP 2.5, and we hope we can calibrate these models with this. That's ongoing work. So next big step in modeling will be including explicit representations of thin fracture zones, and these are upcoming projects. And the biggest challenge I will introduce tomorrow in the other session is understanding supercritical chemistry, because there is no thermodynamic formalism to describe them, and so currently we cannot really model those. Okay, that's all that I have, and I hope I could give you an insight, some basic insight into these systems.